So last lesson we're going to look at this week is 3.4. And 3.4 is on two different things. We're going to learn what's called the rational root theorem, and we're also going to learn how to do synthetic division. So remember, when we talk about rational numbers, rational means that it's a fraction. So what I'm going to show you today is how you can come up with all the roots to a problem as long as they are fractions. If you have a problem where the roots are irrational, then this method I'm going to teach you today will not work. But as long as we have roots that can be written as a fraction, we're going to learn what's called the rational root theorem. I think in your book they might also call it the rational zeros theorem. It means the same thing. Another thing that means the same thing that I want to mention, just while I'm thinking of it, I call what we're going to learn today next synthetic division. Your book calls it Horner's algorithm. I think that's named after the person who maybe figured it out. But we're going to call it synthetic division. And if you look back in the section, they write that. They write Horner's algorithm, and then in parentheses they put also called synthetic division. But if you just look at the homework page, you wouldn't see that. So let's take a look at the rational root theorem. Let's go like that. So if we were looking at a problem, we're going to do this one next. And we wanted to figure out the roots in this problem that could be fractions. Okay, and again, you don't have to write it down because we're not doing it yet. There's only two numbers you have to look at in this whole thing. This number is very important, and so is that one. Nothing else there matters. Nothing else matters at all. So let's see, how do you use those two numbers to find roots that can be written as fractions, or rational roots? So suppose you have some type of polynomial, just like I showed you on the other page. Okay, so you're going to have all these terms filled in. How many terms? Well, depends on what they give you. The one we're going to do next has 4 terms. It is important in the polynomial that all the coefficients are rational. So what I'm saying is you can't have something like this. Yes, that is a polynomial, but you have a number in front of x squared. It's a coefficient, and that coefficient is irrational. So this theorem would not apply to that problem. Can't have any square roots like that. So that would be fine. But all the coefficients have to be rational. And the coefficient of the very first term and the constant at the end cannot equal 0. So if your problem was like this, the theorem I'm about to show you would not apply. Couldn't use it. All the coefficients have to be rational numbers, and the first number and the last number cannot be a 0. So, if a polynomial is going to have a rational root, that means you can write it as a fraction. Let's call the numerator in the fraction p, and let's call the denominator in the fraction q. P and q would be integers, like 3/5, something like that. Well, there is a certain rule for how you figure out p, and there's a rule for how you figure out the q. P will be all the numbers that are factors of the constant. This is the constant. So P, the numerator of your root, will have to be a number that is a factor of the constant. And the denominator of your root will have to be a number that is a factor of the leading coefficient. Now, just to be clear about this theorem up front, this theorem doesn't directly give you any answers. What this theorem does is it gives you a list of possibilities. You then have to use your graphing calculator to narrow down that list. Okay? But without this theorem, you wouldn't even have a list of possibilities. I mean, there's an infinite amount of fractions. Right? At least this theorem narrows down the fractions that could work. But we still have to check and see if they actually do work. Right? Any question on that idea? So again, this theorem is just going to be generating a list of possibilities. That's all that it does. Not every number that we generate in this list is a root. I'm not saying every number in this theorem is an answer. I'm saying it's a list of possible answers. We have to check them out after that. So what we're going to do in the first problem is we're just going to go through and list what the possible rational roots could be. We're not even going to narrow down which ones they actually are. We're just going to write what they could be according to this theorem. So here is our polynomial. And I want to make a list of all the possible rational roots. So the first thing you want to do when you're making your list is identify the p-values and the q-values. So let's go back up and look at what p is. P is a factor of the constant. What is my constant in example 1? Sarah? Negative 6. Can somebody tell me all the numbers that are factors of negative 6? What divides into negative 6? Yeah? 1 and 6. Negative 1, negative 6. That's some of them. Yeah?
Negative 2 and negative 3. Or like positive 2 and positive 3.
Positive and negative 2. I should have spaced this out more. Positive negative 2. Positive negative 3. Positive or negative 6. Those are all the factors of 6. Now, Q. Q is the possible denominators for my root. Q is a factor of the leading coefficient. What's my leading coefficient? Jake? 10. And can you give me the factors of 10?
Positive and negative 1.
Mm-hmm.
Positive negative 2. Positive negative 5. And positive negative 9.
Yes. So this actually is a pretty big, this is going to be a pretty big list. Most problems don't have quite this many. But now, what we have to do is write all of those. All the different numbers you could have in the top for P, and all the different numbers you could have in the bottom for Q. Every combination. So we want to try to do it organized. So this is how I would do it. So this is going to be a list of possible rational roots. So what I usually do is pick one of the p-values, start with that number, and then put that over every denominator you could have. So we could have, these are all the roots we could have with a 1 in the top. 1 over 1. 1 over 2. 1 over 5. And 1 over 10. So if this graph is going to have a rational root with a 1 in the numerator, then it would have to be one of those numbers. Which one? Well, we'd have to check that out using the calculator. But at least we have areas to check out. Let's do the next one. Can somebody give me the rational roots that would have a 2 in the numerator? What would be the first one? Jake?
2 over 1.
2 over 1. What would be the next one? Yes, Jack?
2 over 2, so 1.
2 over 2, which is 1, we already have that one. So we don't have to write 2 over 2. So let's skip 2 over 2. My next one? Yep.
2 over 5.
2 over 5, I do not have that one. And my last one with a 2 in the top. Yep.
2 over 10.
2 over 10, which is what?
1 over 5.
1 over 5. So we already have that one. Right? So those are the only possible roots that are rational with a 2 in the numerator for this problem. The next one has 3 in the numerator, and we don't have any 3's in the numerators. So 3 over 1, 2, 5, and 10. 3 over 1, 3 over 2, 3 over 5, 3 over 10. And let's finish up with the possible rational roots that have a 6 in the denominator. Now, what would be my first one?
6.
Yep, 6 over 1. Francesca, my next one,
6 over 2.
which is
3.
3. So we can skip it. Yep, so we can skip it. We already have 3. Casey, what would my next one be? 6 over 5. I don't have that one. And my last one would be 6 over 10, which reduces to
3 over 5.
3 over 5. Already have it. So that's the answer to the question. That is a list of all possible rational roots. So if you graph that on a calculator, and it is going to cross at a fractional value, it has to be a number in that list. It cannot cross at any fractional values other than the ones you see right there. Okay, any question on that? So it's just a list of places to check. Now, we're going to use that list to try to answer this question. Same polynomial. It says to graph it, prove that it has one real root. Okay, we'll use the calculator to do that. And prove to me that the root that it does have is irrational. Prove that it is irrational. So let's graph 10x to the 5th minus 3x squared. All right, so 10x to the 5th minus 3x squared plus x minus 6. So we're going to graph that. We're going to show that we have one real root. Okay, so we can clearly see there is one real root. But I want to prove that root is irrational. Okay, so let's look at this graph and let's compare where it crosses the x-axis to numbers in our list. In fact, what I'm going to do is I'm going to put that graph on the other page so we can see it easier. Okay, so let's take that, put it here. Let's go through these numbers and let's narrow this list down. Are there any numbers in this list that look like they could be the answer to where this crosses the axis? It's not a guarantee. We still need to check it. Remember, we've seen things that look close to something, but they're not. Yep.
1.
I would say, so this is our list of possibilities. I would say the only candidates from this list, candidates, no, I didn't spell that right today. How do you spell candidates? Candidates. D-A-T-E-S, candidates. I think that's right. You laughing at me? I can't spell it. You can't spell it either. So, all right. So plus 1 looks like a possible candidate for a root. If we check plus a half, no. Minus a half, no. Plus a fifth, no. Minus a fifth, no. Plus a tenth, minus a tenth, no. 2, negative 2, no. This is 0.4. No, doesn't look close to that. 3, negative 3, no. 3 halves is 1.5. No. Negative 1.5, no. 0.6, 0.3, no. 6, no way. That's way over here. Or way over here. 6 fifths, that's 1.2. So I definitely don't think you could argue negative 1.2. But if you said positive 6 fifths, I mean, maybe. I mean, that 6 fifths would probably be like right about there. So it's kind of close to it, but I really don't think it's 6 fifths. The closest one I really think is 1. And that's really the only candidate that makes sense. Now, let's check what it actually is. Second calc 0. Let's pick a point to the left. Pick a point to the right. And do our guess. So, does it cross at 1? No. Crosses at 0.9505. Is 0.9505 one of the fractions in that list? So what does that mean about this number? It's not in that list. Yep.
It's irrational.
It has to be irrational. These are the only numbers that could be rational. And this number is not in that list. It's not even close. It's not any of those fractions. So since that number is not in the list of possible rational roots, it must be an irrational number. And that's what we have to write down. So we got to write that sentence. So what do we call this? F of x. So f of x has a root at 0.9505. You never would have figured that out without that. So f of x has a root at 0.9505, and this number is not in the list of possible rational roots. Thus, 0.9505 must be irrational. That's the only other option it can be. If it's not in the rational, it's irrational. It's like saying, well, if it's not true, then it must be false, right? There's only 2 options. Thus, 0.9505 must be irrational. And that's the answer. So unfortunately, the rational root theorem, we got good practice doing it and writing out the P over Q's. Didn't really help in this problem because there weren't any rational roots. We're going to do some where there are. But that's the idea of the rational root theorem. Okay, we're going to come back to that, and we'll do another example with rational root theorem, but I want to look at synthetic division first so we can tie that in when we do it. So synthetic division is a quick way to divide and get the quotient and the remainder. But synthetic division only works if you divide by something of the form x minus a number. If you're dividing by anything that's more complicated than that, you cannot use synthetic division. You have to go back and use long division. So I'm going to show you guys the steps for synthetic division, and then we'll go through and do a problem. So the first step is to look at the number that comes after the minus sign So block out the x and the minus, look at what you have left, and that number is going to go on the outside of a bracket, just like that. Then, next to it, in these spots, you're going to write down the coefficients of your dividend, of your numerator. I put 5. I don't know if you're going to have 5. It depends on the problem. But you write down the coefficients of your numerator. Make sure you fill in any zeros for missing powers, just like we did yesterday. Now notice here it says coefficients. You're not actually writing down any letters in this whole process. Everything here is going to be done with numbers. So that lessens the amount of writing that you have. Alright, so now the first thing that we do is we're going to end up taking the first coefficient that we wrote down and we're going to bring it down. Okay, so we're going to put a line, and you'll see when we do a problem, and we're going to bring that down. So once we take that and we bring it down, we're going to have something written right there. We're going to take the number that we just brought down, we're going to multiply it by what's on the outside, and we're going to put the answer in the second column. So multiply your divisor by the coefficient you just brought down and put the answer in the second column. Now you're going to have a couple numbers in the second column. When we did long division, what did we always do with our columns in long division? Yeah? We subtracted the columns. In synthetic division, we are going to add the columns. Okay, so we're going to add columns. And once you get through step 3, that's basically one round of synthetic division. Now, you're going to keep repeating that process until you're done. And when you're done, you're going to have a row of numbers on the bottom, like this. How many numbers you have, it depends on the problem. You're going to have a row of numbers. This last row is going to tell you your quotient and your remainder. The number all the way on the right is the remainder. Every other number is part of the quotient. And let's go through an example. Seems confusing to write out the process, but when you actually do it, this is way faster than long division. It's very fast. But remember, you can only use it when you're dividing by x minus a number, or anything that could be rewritten to look like x minus a number. So we talked a little about that yesterday as well. All right, so let's see. Let's do this first. So this is technically example 3 in your notes. It says SD is synthetic division. Use synthetic division to find the quotient and the remainder. Now we're dividing by x plus 3. We're supposed to divide by something that has what kind of pattern? It's not supposed to be x plus a number. Yep.
Minus a number.
It's supposed to be x minus a number. So can we fix x plus 3 so it's x minus a number? Sarah?
Is it x minus negative 3?
Yeah. X minus negative 3. Now we can do our synthetic division. Step 1. Write down the number that comes after the x minus on the outside of that bracket, and then put your coefficients. What's the number that comes after the x minus in this case? Chris?
-3.
-3. Now, let's put our coefficients of what is in the numerator next to it. Can somebody tell me what I would put for coefficients right there? Yeah.
3, 7, 0, 1.
3, 7, 0x squared. That's important. 1. And what's the last, the constant?
-11.
-11. Yep, I'm going to write that one down too. So 3, 7, 0, 1, -11. Put a line like this. Now that I have that set up, I can tell you how much space this entire problem is going to take. Everything is going to fit in that box. It's not going to go down and to the right like long division. So step 1. Bring down the first coefficient. Okay, let's do that. So I brought it down. Now, what do I do with this first coefficient? Yeah.
You multiply by -3.
Multiply it by -3. Okay, I get -9. And it said put the answer under the second coefficient. I just did. Now I have a column. What am I going to do with this column of numbers? Yes. Add them. 7 plus -9 is -2. And now repeat that process. What's -2 times -3? Yeah. 6. And Francesca, 0 plus 6? 6. How about Matt, what's -3 times 6?
-18.
-18. Plus 1?
-17.
-17. What's -17 times -3? 51. Plus -11 gives me,
40.
yeah, 40. Okay, so let's interpret the answer. The answer is that bottom row of numbers. Okay, remainder, 40. Quotient, start with the numbers that are not the remainder. Start with the one on the right and count over and see how many, or what the highest exponent is going to be. That's my constant. X term, x squared term, x cubed term. So it's going to have a 3 in front of the x cubed, -2 in front of the x squared, 6 in front of the x, and a -17 is the constant. And that's the answer. Yes?
So say you were to write it like plus 40 over, like, would you put x plus 3?
Yes.
Or would you put x minus 3?
No, x plus 3 is what is the simpler way to say this. I just did this so people could kind of block the x minus and see what was left. So if you're going to write it the other way I showed you, you would do plus 40 over x minus 3. So, I don't know what I did. I moved something somehow. Okay. All right. Any other questions on that? Well, let's try this one. I want to show that this is a 0. Showing that, well, let me ask it another way. If that number is a 0, it also means that number is a root. It also means that number is an x-intercept. But I'm interested in something else. If 3/2 is a root, what's the other thing that we know about it that we've said before? know, if something is a root, then Matt?
You can plug it in for x.
So I'm thinking there's another, if 3/2 is a root, it means something else. So we had a list yesterday of 5 things. It means it's a root, it means it's an x-intercept, it means it's a 0, but there's something in that list I'm not saying. Yeah?
Factor.
What's a factor?
3/2.
Well, 3/2 is a root. But if 3/2 is a root, then what is a factor here? Yeah, Ethan?
3 is a factor of the constant and 2 is a factor of the coefficient.
Okay, so if you had to figure this number out, hey,
Decades Day.
is it?
I think you got it.
Yeah.
Perfect.
What am I
Talking
dressing?
about that shirt back in like what, 2014, 15? What? Decades Day.
Yeah. Is that good stuff?
Ah. Nah.
You all set?
No.
All right.
Decades Day. I'm trying to get a little
Yeah.
feedback. You know what I mean, buddy?
Yeah. No.
You're not into it, huh?
No. I don't like that.
Good to see you, buddy.
I don't believe in that.
See you at the Hyatt Regency.
You going there? So yeah, if they didn't give you this number, they are giving it to you. But if they didn't, then yes, you'd have to write out all your plus or minus 1, plus or minus 3, plus or minus 1, plus or minus, and then you could figure out that this is one of the numbers. But they're giving that to you. So what's another way of saying 3/2 is a 0? We started to talk about a factor. What would be a factor? Yeah?
I was gonna say it's a solution.
It is a solution to the equation f of x equals 0, but think about it as a factor. Like we did this in one of the homework problems. They said like find a, or no, we did it at the end of class, I think. Find a polynomial with certain roots. I gave you the roots, and you gave me the factors. So 3/2 is a 0. What is a factor? Casey, do you have it? X minus 3/2. Remember, if something is a root, x minus it is a factor. And that's important because look at the last part of this question. They're asking me to factor this. So what I'm going to do is instead of showing 3/2 is a 0, I'm going to show something that means the same thing. I'm going to show that this is a factor. And how do you show that one thing is a factor of another thing? What operation do you use? Remember, how do you show something as a factor of something else? You don't even think polynomials. Like, what if I said, prove to me 2 is a factor of 20? How would you prove it to me? What would you have to do? Yeah.
The remainder theorem?
You would, okay, so what does that mean? Can you explain that?
Like plugging in a number into the equation.
Yep, so one way to do it is to plug in 3/2 and see if it comes out to 0. The only downside to that is it would show that this is a 0, but it wouldn't help me with the second part, which is to actually factor this cubic. So what's another way that you can show something is a factor without just plugging this number in and saying, oh yeah, I got 0. Yeah?
Would it be the long division?
Long division or synthetic division. And to show something as a factor, when you do long division or synthetic division, what do you hope happens? Okay,
That there's no remainder.
that there's no remainder. Bailey's way would have told us whether or not there is a remainder, but it wouldn't have given us this second part. So that's why we're going to do all the actual division and see what happens. So let's put 3 halves on the outside. Let's put 2, -5, 1, 3. And bring down 2. All right. Chris, what's 3 halves times 2?
That would be 3.
3. -5 plus 3, Ethan, gives me,
-2.
yep, -2. And Zach, what's 3 halves times -2?
-6 over 2.
Correct, -6 over 2, which is
-3.
-3. All right, and Tyler, what's 1 plus -3?
2.
2? Yeah, -2. And what's, we just did it, 3 halves times -2 gives me -3. Add them up. A result we already were kind of hoping to get. The remainder is 0. So we've just shown that 3 halves is a 0 of that polynomial. Now, they want us to do that. So, we've done all the work to do that. We just have to write it down. 2x cubed minus 5x squared plus x plus 3. Well, what did we just prove was a factor by doing the synthetic division? Tyler?
3 halves.
We proved 3 halves is a root, so we proved that what is a factor? Factors aren't just numbers. They have to have a whole thing in parentheses. Roots are numbers, though. Yep, Jack?
X minus 3 over 2.
We just proved that x minus 3 over 2 is a factor. That's one factor. Where does the other factor come from? Yep,
The quotient.
it's the quotient. 2x squared minus 2x minus 2. Remember, that's one of the things we learned yesterday. If you know something is a factor and you divide through by it, you get the other factor. I know 2 is a factor of 10. If I divide 10 by 2, that's the other factor of 10, 5. If I divide this by that, I get the other factor. So that is how you would factor it. And notice, once you factor it, the highest exponent in this whole problem now is a 2. Exponents that are only as high as 2, very easy to work with. Worst case scenario, we have to use quadratic formula. We don't have a formula for dealing with problems that have 3's in them. Okay, when the highest exponent is a 3, that's a problem. So the hope is going to be, every time we do a problem where we have to find roots.
I apologize for the interruption. This is just a clarification on sports dismissals. JV girls soccer will be getting dismissed at 1:45 and varsity girls soccer at 2 o'clock. Again, JV is at 1:45 and girls at 2. And varsity at 2, sorry.
So the hope is going to be that when we have a root, we can use the rational root theorem, find a root that we know works. Like in this case, they gave it to you, but now you're going to have to figure out this number yourself using the P over Q. Once you have this number, divide through by it synthetically, and it will turn your cubic into a quadratic. And then you can use quadratic formula and solve it however you need to. Right, but that's going to be the goal. So now let's try example 5. I'm going to skip that one. This is technically example 5. But they're not giving you any hints this time. They're not telling you what number is a root. You have to find it yourself using the P over Q. So the strategies for finding the rational zeros in a polynomial. Step 1 is use the rational root theorem to generate a list of possibilities. Step 2, use the graphing calculator to narrow that list down. Cross out the ones that don't make sense. Step 3, find one that does make sense. There always will be one that works. This won't work out like the first example we did today. There will always be one that works. Divide through by the one that works using synthetic division. And then from there, you'll have a quadratic as your quotient, and then use quadratic formula. Or if you're lucky, you can factor it. You don't have to use quadratic formula. Okay. So, they want us to find all rational zeros of this problem. Can I just plug this into quadratic formula right now and be done with it? It's got 3 terms. Why not? Yeah.
The first term is x cubed.
Yeah, it's not a quadratic, it's cubic. So let's try to find a rational root and then divide through by it, and then we'll have a quotient that's a quadratic. Just like in this problem, or whatever the last one we did was. Okay, so let's start with P. Bailey, what are my factors of the constant here?
1 and 2. Or plus or minus 1.
Plus or minus 1, plus or minus 2. Francesca, what are my factors of the leading coefficient?
1 and 3. Plus or minus 4.
What's my leading coefficient?
Sorry, I was looking at the wrong problem. 1 and 1.
So just
Plus or minus
1. So now if we're going to write all the possible rational roots, Matt, can you tell me what my possible rational roots are?
Positive or negative 1 over 1.
And positive or negative?
1 over 2.
1 over 2. No,
No, just 2. Just
2. 1 over 1, 2 over 1.
Yeah. Okay.
Okay. Now, I have 4 different options. That's a lot less than we had before. Now, how do I check? Or how do I narrow that list down? Yep.
Graphic calculator.
Yep, we're going to graph it. So let's graph. X cubed minus 3x minus 2. So x cubed minus 3x minus 2. And remember, we're looking between negative 2 and 2. That's the biggest and the smallest option we have. What looks like, out of that list, what numbers look like they could be a solution? Yep.
Positive 2.
Positive 2. All right, let's check it. There might be more than 1, but as long as we find 1, we're good. Yes, positive 2 works. I know that if I plug in positive 2, that is a 0. So I'm going to make a list of my roots. Positive 2 is one of them. Now, what am I going to do with that root? This is kind of like the last problem we did now. We know a root now, so what can I do?
Synthetic division.
I'm going to divide through by it. I'm going to pull out the factor x minus 2. I know x minus 2 is a factor. Divide through by it, get rid of it, and look at what you have left, and that will be your other answers. So 2, and then we've got 1, 0, negative 3, negative 2. Moving down to 1. Casey, 2 times 1?
2.
Plus 0? 2. How about Chris, 2 times 2?
Is 4.
Plus negative 3?
Is 1.
1. And Tyler, 2 times 1?
2.
Plus negative 2?
0.
0. So we just confirmed what we already knew. But what I'm more interested in now is that. Now, set that equal to 0 and solve it. So x squared plus 2x plus 1 equals 0. That will be the other answers to the original problem. But why is this a lot easier to solve now than the original problem? Yeah.
Because you can use the quadratic formula.
Yeah, I can use quadratic formula. In fact, this one even factors. You can factor it and not even have to use quadratic formula. Can someone tell me how it would factor? Francesca?
Would it be x plus 2, x plus 1?
The x plus 1, I like that one. And then we have to multiply by another number here that would give us 1. X plus 1. X plus 1 times x plus 1 would give us what we have there. Which means, what do you plug in for x to make the first parenthesis 0? Yeah? What about the second parenthesis? So -1 is what we call a repeated root. It makes two different factors 0. You don't have to write it twice. We just have to make sure we write it. So x equals -1 and +2 were my roots. You might say, well, yeah, could we just look at the graph and figure out that it was at -1? Yes, in this problem you could have. But the problem would have been if the directions said something like this. Find all real answers. You may get a number that comes out to like 0.9505, right? Like we did in the first example. And if I say to give it as an exact answer, 0.9505 is a decimal, that's not exact. The only way to get an exact answer is to use quadratic formula. So let's try on this one, and this will finish us up, and let's see what happens. Okay, so first thing I do is look at the highest exponent. What type of equation is this based on its highest exponent? Yeah, it's a cubic. We don't have a formula for dealing with cubics. Is there a formula? Yes, there is. You wouldn't like it. It's very long. So the only way we can deal with a cubic is to turn it into something that's not a cubic. We have to be able to find a rational root and divide through by it. That's our only chance. If there is no rational root, then you're not going to be able to do this problem. I haven't taught you anything that would help you. But there will be a rational root. All right, Ethan, what are my factors of P?
P would be 2 and 1.
Yep, plus or minus 1, plus or minus 2. And Jake, what are my factors of Q?
Plus or minus 1.
Plus or minus 1, plus or minus 3. So not as easy as the last one, but not as bad as the first one. So list of possible rational roots. Okay, 1 over 1, 1 over 3. 2 over 1, 2 over 3. So that's technically 8 different numbers that could be rational roots. I don't really want to try all 8 of them one at a time. It's going to take me a long time to do synthetic division by guessing. So how can I narrow this list down quickly and figure out which one I should try? Yep.
Graph it.
What did you say?
Graph it.
Oh, graph it. Yeah. So let's graph it. And figure out the remaining candidates that could be an answer. 3x cubed minus 8x squared plus x plus 2. So, out of the numbers in our list, which ones look like they could be a root? Now?
-1 over 3.
Yeah, I would say -1/3 could be. We're going to have to check it out. So these are the candidates. And then anything else there that looks like it could be a root? Yeah?
Positive 2/3.
I think positive 2/3. Let's check, let's just check positive 2/3. That's the root. Let's check negative 1/3 just to see. No, not a root. So negative 1/3 was close, but that doesn't come out to 0. So that may give us a hint about what kind of number this is going to be. This one is not in that list. So that means it's probably not that type of number. Okay? So let's go with the one that did work, which was 2/3. So let's make a list of answers. Okay, we know 2/3 is going to be an answer. Now, let's divide through by it and turn our cubic into a quadratic, and then we're good. 3, negative 8, 1, 2. Bring down to 3. Zach, what's 2/3 times 3?
6/3. So, 2.
2, yep. Negative 8 plus 2 is negative 6. Somebody else tell me what is 2/3 of negative 6? Yep.
Negative 4.
Negative 4. Add it to 1, we get negative 3. What's 2/3 times negative 3? Yeah.
Negative 2.
Negative 2. Just confirmed what we already knew. I wasn't interested in the remainder. I was interested in this. This that I have circled is going to tell me the other two answers. Now, that is not going to be factorable. That's 3x squared minus 6x minus 3. There is something you could do with that to make the numbers a little smaller. Still not going to be factorable, but does anybody see what you could do there? Ashley?
Divide by 3.
You could divide everything by 3. Again, it's still not factorable. So how do we solve something when it's not factorable? What do we have to use?
Quadratic.
We're going to have to use quadratic formula. So A equals 1, B equals negative 2, and C equals negative 1. So let's finish it up and see what we got. Negative B plus or minus the square root of b squared minus 4ac all over 2a. Now we just have to clean that up a little bit. Minus a minus becomes a plus. What's 4 times 1 times 1? Yeah. Plus 4? 8 over 2. And how can we simplify the square root of 8? Matt?
Wouldn't it be 2 square root of 2?
Yes, 2 square roots of 2. You can split up square root of 8 like this. Square root of 4 times 2, that is 2 square roots of 2. Now, everything there has a 2 in common, not under the root. So divide that by 2, that by 2, and that by 2. So the final answer for the other two roots are 1 plus or minus square root of 2. 1 plus or minus square root of 2. Now, just to show you, let's check the one on the right as a decimal. And I don't know how well you can read it, but it says 2.414. Watch what happens if I type in 1 plus the square root of 2. 1 plus square root of 2. Put in the plus sign. 2.414. It's exactly the same thing. The calculator cannot tell you this. It will tell you a decimal, which is not what I'm going to look for in that kind of problem. Right, so you have to use quadratic formula. All right, any questions on that? Okay. So tonight, there is no homework from the book. Let me explain tonight's homework. Take home. The take home will cover sections 3.2 and 3.3. Tomorrow's part of the test will cover 3.3 and part of 3.4. Take home will be due at the beginning of class tomorrow. So that will be due at 12:30 p.m. on October 15th. That's Eastern time. Well, I've done this before. So it's due 12:30 p.m. Eastern time on October 15th. It will be on Edulastic. If not done by 12:30 p.m., it equals a 0. The grade would be a 0. If you do not agree to the above conditions set forth, then you can take the test in class at a different time. Take in class. So that means if internet goes down and you got to figure something out between now and 20 hours from now. Okay? Again, if that's a problem for anybody, you are more than welcome to take it at a different time in class. I will put a time limit on it, probably about 1 hour. You'll have 6 questions. I think an hour should be plenty of time. Usually you do a whole test in an hour. This is half of the test. Yes?
I'm confused. Is that 12:30 standard?
That's Eastern
Eastern?
Is it just standard
Time.
time or Eastern Daylight Time?
Eastern time.
Okay.
Yes. Is anybody not doing the test part 1 as a take home? No objections. Perfect.